Welcome everybody. This video is for the Biophysical Society annual meeting in February 2021. In this video, I'll be summarizing teaching materials that I've developed for modeling the COVID-19 pandemic in the United States. The teaching materials are designed as guided inquiry exercises where students discover for themselves the consequences of model assumptions by implementing them in a simple spreadsheet model. Okay, so let's start by talking about where you can find the materials. They're on the web at circle4.com/biophysics. This is the home page for the project, and if you click on the free sample chapters link, it'll take you to the sample chapters for a book that I'm working on with Cambridge University Press. Chapters 1, 2 and 3 are here at the top, but the main topic of this video will be Chapter 12. But before we do that, let's go to Chapter 1. Okay, so here's the cover page for the draft book, and one of the things that I'd like you to pay attention to is the finite difference diagram. It's one of the main features of the book that we'll get to when we get to Chapter 3. Now, one of the main reasons that I wanted to talk about Chapter 1 is to let you know that it covers preliminary stuff that students will find useful. The main topic of the chapter is the marble game, which is a kinetic Monte Carlo simulation of diffusion. Marbles jump from one box to the other using a random choice selected by a die that simulates diffusion. The other main purpose of the chapter is to introduce students to how Excel can be used for quantitative modeling. The chapter starts right at the very beginning with how to enter things into cells and how formulas work. It then moves on from there. Chapter 2 is primarily about introducing students to the idea of writing an algorithm. Here's a handwritten algorithm. It has various features. The parameters column lists the constants for the simulations, and they go in column A of the spreadsheets. We then have a list of variables which become column headings in the spreadsheet. Step 0 sets up the simulation, and step 1 is the main part of the algorithm that's repeated in each row of the spreadsheet. One of the things I like to make a big deal about is getting students to do unit checks, which are important in biophysics and the life sciences in general, because it's common that the units that are used are not standard SI units, at least in the United States. And so students always need to pay attention to those when they're doing quantitative modeling. Chapter 3 is primarily an introduction to using finite difference methods. An important part of that are finite difference diagrams, which indicate the rates at which marbles jump from box 1 to box 2, or from box 2 to box 1. Those rates can be used to derive a finite difference equation. The minus indicates that marbles are leaving box 1, and the plus indicates that marbles are entering box 1. That equation can be rearranged to give a simple FD equation, finite difference equation, for the small change in the number in box 1 during a small time increment, the time step. So here's chapter 12. It's the chapter that we're going to spend most of our time talking about. After some introductory comments, we start out with probably the simplest possible model of epidemiology. It's what I call an unlimited growth model. The way that it works is that you've got the model population split into two groups, susceptible people and infectious people. Those are the only two choices. The arrow indicates that people can go from being susceptible to being infectious, and that's really the only thing that happens in the model. And so people can jump from box S to box I. The arrow is labeled with an expression. Ki is the infection rate constant, and Ni is the number of people in the infectious box. In question 1, we go over how to write an algorithm, and there's a separate YouTube video about how to do that if students have trouble. They start out by downloading a pre-formatted spreadsheet. With that spreadsheet, they're able to generate a finite difference model of the unlimited growth model, and then to eventually compare it with USA data. So here on the y-axis we have the new infection rate Ri given in confirmed cases per day, and that's plotted against time in days. As you can see, the unlimited growth model does a pretty good job of predicting the shape of the curve for the first 19 days or so. Section 2 of the chapter introduces the finite population model. It has the same two boxes. The only difference is that the infection rate includes this term lowercase s, which indicates the fraction of the population that's susceptible to being infected. It's the number susceptible divided by the population size. Changing to the finite population model allows us to talk about how the curve can be flattened by social distancing. Section 3 introduces the SIR model. It's the same as the previous models, except that we've now added a third box for people who've recovered from COVID-19. As a result, there's a recovery rate constant, and it's multiplied by the number infectious to give the rate at which infectious people recover. The SIR model is both the origin of the basic reproduction number, which indicates how many people an infectious person can infect, and the concept of herd immunity. When you fit the SIR model to the first 19 days, it predicts a rather alarming exponential growth that eventually tops out at about 2 million infections per day. I call this the exponential dragon. On a semi-log graph, it has a rather characteristic inverted V shape that we'll talk more about later. Another feature of the SIR model is that it can show extreme sensitivity to initial conditions. This graph shows what happens if we adjust the fitted data by just one day at a time. It produces a series of 4 graphs that show quite a dramatic change in qualitative behavior. There's also an exercise where students fit data to the first 2 weeks of April and show that it successfully predicts what happens all the way to Memorial Day. Section 6 introduces a method to model the transition from exponential growth to the period of social distancing. Using that model, with the assumption that the whole of America behaved like New York City, students can predict how many lives could have been saved if everybody in the US had done it New York's way. A key part of that analysis is to get students to model the transition from the initial exponential growth to the period of social distancing using a Gaussian transition function for changes in the infection rate constant. The same techniques can also model the summer surge and the beginning of the fall surge. Model population size is a key feature of the model. It only matches the actual population of the United States if every person who got COVID-19 is included in the official case count. Current estimates are that about half of COVID cases are asymptomatic and are not reported. In addition, there are people who have mild cases of COVID, but they never got tested, and so are not included in the official count. All of that means that the reported cases may only reflect as little as 25% or even less of the actual number of cases in the US. The way that can be accounted for in the model is to make the model population a corresponding fraction of the actual US population. This figure shows a fit to the reported population up to Thanksgiving Day, together with the prediction for a model population that's 25% of the actual population. The dashed lines correspond to a model population of 10% and 50% of the actual population. Again, all three graphs show the characteristic inverted V shape of the exponential dragon. The data in the holiday period from Thanksgiving through New Year exhibited large fluctuations, which is why I included a 7-day moving average of the reported data, which is the jagged black line in the graph. This figure uses the same model as the previous graph, but now the model is fitted to reported data up to the end of the 2020 calendar year, with the added feature that the size of the model population is now an adjustable parameter. The fit corresponds to a model population of about 15% of the actual population. When I first did this fit, I was hopeful that the prediction was correct, but the effects of the holiday season weren't over. This FD diagram shows how vaccinations can be incorporated into the SIR model. The only quantity that's required is RV, which is the effective vaccination rate, which is the rate at which susceptible people, in box S, are vaccinated. According to the model, people who have had COVID-19 and are recovered are already in box R, and their vaccinations make no change to the model. This figure shows the effect that vaccinations can have on a period with a static infection rate constant. The orange curve is the same as the curve from the previous figure, with a model population of 50% of the actual population, and we're assuming that they're not vaccinated. The dotted red line represents the effect of vaccinations at the rate predicted for the Pfizer BioNTech vaccine alone. The blue dashed line corresponds to vaccinations at just over twice that rate, and the green dashed line is for twice that value. This figure shows how the fit with 5 infection rate constants changes when data up to inauguration day are included, and the fitted model population size expands to about 25%. And this figure shows the fit with an additional 6th infection rate constant to go with the slower increase during the holiday period. In conclusion, there are many activities that students can do based on these materials, which you can find at circle4.com/biophysics, and you should look to the top of the page for the link to the free chapters and videos.